about this. All right, so chapter 2 is over. Chapter 3. Finally, we're talking about systems in general that we can handle. Linear systems. And the first thing we will start is actually the properties. The linear system and the linearity. Principle. Okay. The first thing we want to focus on are the easiest case, which actually has a lot of ideas inside. That is linear system with constant coefficient. Okay. More or less, it's something look like this. Where A, B, C, D are constants. Why do we care? Well, this is the only system that we can write it into a matrix format. Prime prime, which is roughly something like okay, that's why we care about this. If you start to take some of the A to be not T, not constant, but make it a T square, all you do is just you go to this matrix and change it to be T square, which is not constant coefficient anymore, but still you can write it into a matrix. However, the matrix you write down will depend on T now, which is kind of harder to handle. That's why we force all these things should be just constant, no function of T. Okay. You also want something like that, but no plus E plus F, even though they're constant. The reason is because if you do that, you have to add a tail here. That means you need to add another vector here, even though it's a constant. So if you add those kind of terms, the whole thing will not be homogeneous anymore. Okay, so if you think about it, what we're dealing with is nothing but the easiest case, which is number 1, autonomous. Number 2, homogeneous. That is very important for what we just did. Okay, so no T square, they have to be a constant. This one has only numbers in, no functions of T. Later, of course, you can generate the idea here. The third thing we want to talk about is we did those kind of systems before, right? It's 2-dimension. But now, if you look at this format, you can clearly have a 3-dimensional vector XYZ, or 4-dimensional, or 5-dimensional, even 1,000-dimensional of linear systems. They can all be handled in the same way. So we're not going to be restricted with only 2 variables anymore. We have dimension of the system. We call it n. It basically represents the length of the vector y. let's say dimension of y. This is going to be n by 1. Okay. This a is always going to be n by n. And the reason is because this y here is also n by 1. For example, this is a two-dimensional system. Okay. Depending on how big the matrix is. Okay. All right. So everything we learned before, are they linear systems? Well, we have predator and prey. Are they linear? Up to this point, no, not linear. Because of R times F. SIR. The moment you see this, not linear. What else do we left for systems? Damped. Harmonic oscillator. All right, this one looks like well, P and Q are constant. You have V, you have Y. This one is a linear system. Okay, so everything we learned so far, only damped harmonic oscillator is linear. We will, of course, use this one as an example again and again to illustrate the ideas. Some more concepts we had before, which we talk about, the decoupled system and partially decoupled system. I just want to put it here, so we already know this means a diagonal. A is diagonal. This means A is triangular for our case. Either upper or lower triangular. All right, that's the basic setup. Nothing particular here. Just a matrix form. Now let's talk about equilibriums. Of a linear system with constant coefficient. So well, what do you mean by equilibrium? That's when the derivative becomes zero. You go there, you stay there because you don't change. How do you find it? You set the right-hand side to be 0. So for this case, you basically set AY equals 0. That would be your equilibrium. Later, we will talk about how to do the sink and the source. Basically, it corresponding to the eigenvalues. But for now, it's just equilibriums. Then, of course, what are you looking at? You're looking at something from linear algebra. A matrix times a vector equals 0. This corresponds to a homogeneous linear algebra problem. What's the solution? The solution will be the kernel space. That's where the connection start to make. Where is your equilibrium? It's all in my kernel of my kernel space of A. All right. Then the following concept will be what I write down for equilibriums, but basically it will be what I write down for linear algebra. Okay. Let's see if you can reflect what is trying to say. Number one, this one is always solvable with a trivial solution. That solution is y equals 0 because A is linear. Remember the harmonic oscillator? Do you have equilibrium? The answer is yes. At least you have one equilibrium. That is 0, 0. Why? Because this is a trivial solution. Okay. Number two. Other than the trivial solution, do you have other solutions? Which called non-trivial solution? Take some time. Go to your memory of linear algebra. You should at least reflect one way to tell, can this one be solved with nonlinear equation, with nonlinear solution? You should actually have maybe 5 or 6 different ways of telling it. Any ideas? Do you remember that if something is solvable is closely related to if A is invertible? I'm just going to write down several ways for you to think about. A is invertible. Okay. It has something to do with the rank of A. It has something to do with, are the columns of A linearly independent? This is actually rank A equals N. Okay. It corresponds to a pivot in every column when you do echelon form. This corresponds to if the column space of A is the whole Rn, and such. And also determinant of A cannot be 0. Okay, hopefully reflect some of them. If you don't, go back to your linear algebra and check what we mean by that. Everything I wrote down is equivalent. Saying one thing is the same as saying everything else. Okay. If you put all these together, they all mean the same thing. Under this circumstance, it will imply AX equal to 0 only have 0 solution. That means your linear transformation defined by A is 1 to 1. That means all the columns are linearly independent. That means your whole matrix is full rank, such. Okay. That also means if you're looking for a non-trivial solution, you just need to check if one of them fail. Okay. Now I'm going to write it down. That is number, non-trivial solution theorem. We have all these kind of ways to check. We will take the easiest one. That is the last one. Then the only equilibrium for is the origin, which is 0. The key is the determinant A does not equal to 0, which means A is invertible. Okay. Of course, we can quickly check. This is the damped harmonic oscillator. Okay, clearly A looks like. Let's not do this. Let's write the whole thing down. Y V prime equals Y V. Okay, now 0, 1, -3, -2. Okay. So question 1, does it have equilibrium? Equilibrium. The answer is yes, at least 0. The trivial one is always there. Number 2, does it have any other equilibrium which is non-trivial? Then you just use the theorem and check the determinant of A. What is it? It's positive 2. Is it 0? Not 0. Therefore, no. Okay. 0 is the only equilibrium. So don't even bother to find others. It may look like a new theorem, but really it's just we're exercising what we had in linear algebra of solving homogeneous linear systems. The book only gives you the determinant, but you have all the rest. Okay. Any questions so far? Good. Now number 3. What if determinant A equals 0? Well, in that way, we have non-trivial equilibrium, of course. Okay. But that's not the essential point. The essential point is the whole thing is called degenerate. Did you guys went over degenerate in linear algebra? Okay, this is what it says. Now let's talk about linear algebra, right? Yeah, you have an A, fancy. Okay, we're basically talking about, is this one solvable in general? Sounds good. Is it doable? Well, it really depends on how many variables you have and how many equations do you have. Judging by the look of it, I assuming there are 2 variables, there are 2 equations. Sounds good. So if you have m by n 3 by 2, in general, it's not solvable because you have more equations than variables. Okay, if you have a 3 by 2. More equations than variables. In general, not solvable. That's why you need to do linear regression. If you have 2 times 3, that means you have 2 equations, 3 variables. At least you have 1 free variable, possibly 2. Always not unique. Make sense so far? Okay, if all the information are presented to you like this, usually that's how we judge. Okay. Now what's tricky is sometimes you may look like there are 3 equations, but actually you only have 2 because some of them are redundant. For example, something like this. Do you have 2 equations? Yes, I do. Do you have 2 variables? Yes, I do. Okay, seems like it's a nice combination. However, if you just go a little bit inside it, you times the first equation by 2, what do you got? And the second equation? If you do an echelon form, you will find you will have something all 0. Make sense so far? Okay, that is the case we call degenerate. Even though you look at the thing, you think you have 2 equations, but actually you only have 1. You have fewer information because a lot of information are redundant. Okay, or if you give me a lot of column vectors, you give me 3 column vectors, I'm supposed to have a 3-dimensional column space. But if you give me a 2-dimensional column space, that means the 3 vector, one of them is redundant. It is a linear combination of the other 2. Still okay? That is degenerate. You don't give me all the information. Of course, a quick way to check it is check the determinant. Does it make sense to everybody, roughly? You give me a 5 by 5 matrix. Is it really worth 5 by 5? Maybe it's a 4 by 5. You have one redundant one, right? If you have that case, degenerate. Okay. Later we will see degenerate give us trouble when we try to solve the system, simply because you cannot generate a full basis from here. So you cannot have the whole solution. All right. Third, linearity principle, or you can call it principle of superpositions. Idea is quite easy. Okay. One, if y t is a solution of this, then so is c times y. Number two, if y1, y2, both are solutions, so is y1 plus y2. Okay, it's very easy to verify. For example, for the second one, if y1 satisfies this, if y2 is satisfied this, you simply just add the two. On the left, you have y1 plus y2, which is the new solution. Certainly satisfies A, y1 plus y2. Okay. So y1 plus y2 also satisfies this. Thanks to the matrix operation is linear. So the key here is because these two are linear. That's again another reason why do we only consider linear systems with constant coefficient. Or more precisely, ax plus y equals ax plus ay. They come from this property. All right. You times it by a constant, it's fine. You have two, you add them, you minus them, it's fine. Of course, that's not interesting. The interesting part is the general solution. Of a linear system. Okay. I will write down what's in the book. which only works for 2 dimension, but we can generalize. Suppose y1, y2 are solutions of dy over dt equals a1. Okay. And if y1 0 and y2 0 are linearly independent, okay, then for any initial condition y0 equals x0, y0, we can find constant k1 and k2 such that k1 y1 plus k2 y2 is the solution to the initial value problem. In this way, we call the general solution constants, the general solution of the system. Well, the theorem looks really fancy here. It's long and it's not the best wording I've seen. Whatever. Okay, basically what this one says is you just find several basic solutions like y1 and y2. Your general solution will be all possible linear combinations of y1 and y2. Why? Because of the linear principle. Okay, if y1 is, y2 is, then y1 plus y2 is. If y1 is, a constant times y1 is. Therefore, any possible linear combination of y1 and y2 will be a solution. Sounds good. Moreover, for a two-dimensional system, you only need 2. That's what the theorem says. All right, let's see example. Okay, number 1, let's see the undamped harmonic oscillator. Let's just take this one as an example. We have a system. Okay, if we write it down, something is wrong. What did I do? Okay. Linear system with constant coefficient. So it satisfies y prime equals ay. All right. Do you know a solution? Well, I do. Cosine t, sorry, y1 equals sine t, which means v1 equals cosine t, which is y prime, which gives us the first solution. This one work. Meanwhile, by guessing, this one also work. Good so far? So we have two. Okay. What do we want? We want to say the general solution looks like this. For any arbitrary constant k1, k2. This is what we want. So we don't even bother to find the third and the fourth. You just say, hey, these are all the possible ones. Still okay? Now, the only thing stopping you from doing that, according to the theorem, is you need to show they are linearly independent. Moreover, you don't have to show it in general. You just need to show they are linearly independent when y equal to, and when t equals 0. So sine 0, cosine 0. Is 0, 1 and 1, 0 linearly independent? The answer is yes. Especially if we have two vectors. You just check if this one is the multiple of the other one. Therefore, the solution looks like this. The rest is give me an initial value. Once you give me an initial value, I can find what K1 and K2 exactly are. For any initial value, I give you the corresponding K1 and K2. Therefore, this one works for any initial value. That's why it's called the general solution. It doesn't matter which initial value you have, the format looks the same, just with different constant. Of course, how did we find the first y1 and y2? Later we will show how to do it efficiently. For now, we just guessed. Okay, happily this one worked. But later, we need a better way of solving this, finding those y1 and y2. Okay. The good news is 2 of them is enough. Moreover, you know what the rest looks like once you have 2. The rest will be just all possible linear combination of the two. Okay. That's all for today. Stay if you have questions.